In this example, I will show you how to calculate heat for energy in non-reactive process. Given a gas mixture containing 20% methane and the balanced air flowing into a heater, based on that, I can start drawing flow chart. (20% methane, that's 0.2 mole fraction, and the balanced air is flowing into a heater. Well, because in the heater there's no reaction going on between the gas species, there's no need to break down the composition of air. Then just consider air as one species. Volumetric flow rate is 1,000 liters per minute, and this is standard temperature pressure condition. Input temperature is 25 degrees Celsius, output is 275, and pressure is constant, that's 1 atm. And we need to calculate the heat input in kilowatt. Well, from there, I can write down assumption to let people know what I'm thinking to run my calculation, and this way I can cancel the terms that are negligible for the energy balance equation. And then first of all, I'll talk about this heater, not in a reactor, so there's no reaction. It's non-reactive process. I just simply say no reaction. And while given STP, and then based on the condition given, I can say this is ideal gas. And the heater has no turbine, so I can say there's no shaft work. And also, it doesn't talk about any flow work or boundary work. I can also ignore the boundary work. In the book also say flow work. That is the work causing the boundary expansion or shrinking during work. And I can also neglect the kinetic energy chain and potential energy chain because it's not talking anything about change related to kinetic energy, and there's no position change. Then I can also ignore potential energy change. Next, because it's talk about there is mixture flowing into the heater, flowing in and flowing out, so there's a material exchange going on in the system. Then obviously this is an open system. Because the open system, I also assume that it's continuous state and steady state process, so nothing changed with time. In this way, it's easier for me to calculate. Okay, based on that, I can start writing material balance and energy balance equation. And because where we say this open system steady state, for material balance on open system is simply input equal to output, and our basis based on the problem statement, that is 1,000 liters per minute, and given its standard temperature pressure condition, we can convert that to mole number for the gas mixture. Because of that, and then we say it's ideal gas condition. Based on what we learned in chapter 5, we can convert from volumetric flow rate to molar flow rate using standard condition conversion factor. We have 1 mole equal to 22.415 liter at standard temperature pressure condition. That is 44.6 mole per liter. This is the molar flow rate for the air mixture. Then we have 20% methane, 80% for air, and we can calculate the molar flow rate for both species as well based on the mole fraction given. It's 0.2 methane times the species mixture volumetric flow rate and had a unit mole per minute. Well, you can convert that to second, but I just keep them as mole per minute first. I can convert it all the way in the end when I run the calculation for energy. Molar flow rate for the air is 80% of the total. Then that is 0.8 times the total molar flow rate. That's 44.6 again. Then I have 35.69 and then round this to 35.7 mole per minute. Okay, now I have the material balance. Next step is writing energy balance based on the system. I have an open system. Energy balance for open system is simply using, well, in the book it put heat plus work first. I like to put the system energy on the left equation, keep it consistent on chapter 7. For system energy, that's enthalpy change plus kinetic energy change plus potential energy change equal to heat flow plus work flow. And based on the assumption that can start to cancel our term, obviously there's no kinetic energy change, no potential energy change. These two guys go out. And then we can kick out this guy as well. Then our net energy balance equation is simply enthalpy change equal to heat flow. And this about heat flow. Then we can start from there. We know the enthalpy change equal to mole number because this guy had the units kilojoule, right? And then we had to use mole number times specific enthalpy change, and specific enthalpy change had the units kilojoule per mole. And then I can use heat capacity to calculate specific enthalpy change. Before I do that, I need to set a reference state that is something for my initial state. And we had two species in this problem statement. We had to write reference state for all the species. Now we have methane, that is gas phase. And I like to choose the temperature pressure condition in my inlet stream. In this way, if I calculate outlet, I simply minus inlet. And I can set the reference temperature, pressure, and the specific enthalpy is simply 0 for the reference state. Again, L is gas at 25 degrees Celsius, 1 atm. That is my reference state. Now I need to draw a table for all the species and listing the mole number as well as specific enthalpy. And then I have to write the species again. And the molar flow rate in the input stream equal to output stream. Because of this, we have molar flow rate input equal to molar flow rate in the output stream. Then same for all the species and the input stream. Well, let's write down the unit first. That is mole per minute. And then we have 8.93. L is 35.7. We just calculate this part. And then we have to list specific enthalpy. Specific enthalpy, or sometimes you also call molar enthalpy, whatever you like. That is kilojoule per mole in this problem. Although there is another unit for specific enthalpy, if you have mass flow rate, then you can have kilojoule per kilogram. In this problem, it's kilojoule per mole. And again, write down the mole flow rate in the output stream, and the unit is mole per minute, and specific enthalpy again in the outlet. Okay, now I start to fill out the table because I say the inlet stream I use is as reference. The specific property in the outlet stream is simply 0. Inlet stream, because I choose as reference state, and the molar flow rate is the same input and output. Just simply copy that. If it's not the same based on the system, then you have to calculate that. And then I don't know the enthalpy in the outlet stream. I simply use the variable to represent, then I can calculate them later. Now I had the table, I had the reference day. Next step is to calculate the unknown specific enthalpy in the table. For methane species, we had to use heat capacity and specific enthalpy change. Well, this is actually change. Okay, that is starting from 25 degrees. That is the starting temperature because that's the temperature I choose in my reference day. Therefore, I start from that temperature, and the outer string I had 275 degrees Celsius. That is the final temperature. And in this case, we're gonna have constant pressure, and we had to use heat capacity at constant pressure. C sub P, and this is methane. We have to look up in the table B2. Then there's two ways to write the equation for specific enthalpy change. That is integral, while also the heat capacity. The heat capacity. For heat capacity, there's two functions. I prefer the second way in the textbook in table B2 because of less calculation. And then simply had to look for A, B, and C constant from table B2. Again, this from table B2. Table B2. Okay, now I have A, B, and C times 10 to the negative 3. This is 5.469 times 10 to the negative 5. And 0.3661 times 10 to the negative 8. And using TI-84, I can calculate the change of specific enthalpy from 25 to 275 degrees again, and write down the equation dt and substitute the constant into this equation, and I got 10.628. If you do not know how to use scientific calculator to calculate the integral from initial temperature to final temperature, I have a video for that. You can go ahead to watch that. Now I have delta H1. That is for methane. Mark this up. Okay, now we have to look for delta H2 for L. The good thing is for L, you can look at in the table B8. Let's go to table B8. Where's my table B8? Right here. There you go. I need to look for 275 degrees Celsius, but I don't have this in the table. And I had 200 degrees, 300 degrees for L, and then I can do interpolation based on that. The way to do interpolation, I also have separate video to explain that, but I will show you because I need to do the calculation anyway. So from the table B8, we have L and delta, specific enthalpy, right? Yep, 5.15 and 8.17, 200 degree, 300 degree, 8.17. Why? Because the specific enthalpy, you follow a linear curve, and we can simply draw a curve like that, starting from 200, 300. This is the value I can find on the table because I'm looking for 275 that is unknown, and my y-axis is h hat. The x-axis is temperature in degrees Celsius, and 300 we have 8.17. At 200 I have 5.15, and 275 we don't know. That's what we're looking for. And then we can do, well, because on the same curve, linear curve, the velocity, because on the same linear curve, the slope is the same from this point to this point. or from this point to this point, velocity slope is from here. Therefore, we can have based on that information, we can have from 300 to 275, that is the delta y, over delta x is 300, is delta x, equal to from 300 to 200, delta x, delta y. So my delta x is 300 to 200. My delta y is 8.17 minus 5.15 here. Now I only have one variable. I can simply solve that easily. Then I have, this is again 2. That is 7.415. And it had the unit kilojoule per mole. This is for air. Okay, next step. Go back to the energy balance equation. We had this net equation that is change in enthalpy equal to heat, and we say that change in enthalpy equal to sum of outlet stream mole number of each species times the specific enthalpy. This is outlet minus inlet stream mole number of the species times specific enthalpy. Okay, now we can fill out this equation, substitute with the number we just found. The mole number, let's start from methane. We have 8.93 based on the table. 8.93, that is the molar flow rate in the inlet stream, and the unit is mole per minute times 10.628. We just calculate that using the integral of heat capacity. That is methane. And we have to plus the air in the inlet stream. And for the air, we have 35.7 mole per minute. Again, we have found that times the specific enthalpy. We had just found that as well. That is, I'm sorry. Yeah, this is output. This is inlet. This is outlet stream, because we have to use outlet stream minus inlet stream. Inlet stream is supposed to have 0, so 415 kilojoule per mole minus inlet stream, because heat capacity, because specific enthalpy in the inlet stream is 0, then everything times 0 is 0, right? Now this is for the outlet stream, and this is the inlet. There we can get 359.6 kilojoule per minute, because based on the units I have. However, I need to convert to kilowatts, so for kilowatt is kilojoule per second. Simply convert from minute to second. 1 minute is 60 seconds. Then I have 5.99 kilowatt. That is change in enthalpy. Okay, because of net equation, we have change in enthalpy equal to heat based on the energy equation. Well, if you want, you can write equation 1. Based on 1, we have this equation, and therefore heat flow or required heat input is simply 5.99 kilowatt. That is the final answer.